Okay, let's look at the circuit here. So, is it increasing, storing, or decaying current? Is it increasing? Because you could imagine the following thing here. I imagine that current's probably flowing this way. That would be my guess. And I think that's a good guess. And then I have current through that inductor where it's going to be coming in like this. So I would assume here that these two currents have to be opposing each other, therefore reducing the current through the inductor. When I throw the switch and I kill this off, these sources are only applying current to that, and it should be doing that. Now note, this guy's a fairly straightforward calculation because we see that the 24 ohm resistor is in series with the inductor, so we know that that has to be, what, 24 times the current of the inductor. So calculating the current of the inductor is the same as solving for V24 as far as I'm concerned. What's different here, though, is what? You've got to solve for the initial conditions. Okay? You've got to solve for the initial condition. And you'll see that in the next circuit, we'll play a role of doing those two things here simultaneously. Okay. Apparently I don't know what I'm doing. So, what do we want to do? Just think broadly, and then you worry about the details. You got to do what? Use KVL or KCL, or both, to connect IL to VL. Once you do that, check your equation. To check your equation, one technique that you can do here is that you can immediately determine what the current of the inductor is going to look like as it goes to infinity. That should then give you the steady state value, the final steady state value should come out of your equation for this circuit. Check your equations. You'll see that's of paramount importance in chapter 9. Then, we write down the assumed solution. Okay, from that assumed solution, solve for the B's. Once I get my B's, I solve for the initial condition. From that initial condition, I get my constant A. And then I go back and I solve the circuit problem. Let's do it. So, first thing that I want to do here is that I want to look at step 1, where I want to derive first order equation and do a check on it. Okay. So here we go. So the first thing I want to do here, note that the switch is closed, so therefore there's nothing there. So after switch is thrown, we get a circuit that reads like this. So this guy is now live. So I get 8e to the minus 5t. I have 32 volts. I have this resistor, and then I have this inductor. So I have 24 and 8 Henry, and I know that I have this current right here. So what am I going to do here? Immediately, I'm going to apply KVL. Why? They're in series. So then I'm going to apply KVL to connect IL and VL. So here we go. So note that I can combine these two sources, so I just have a very nice KVL equation. So when I do that, let's look at this. So I'm going to get what? I'm going to get 24 IL, right? 24 IL, plus this inductor has a current running through it. Oops. My mistake. Should be VL. And then I'm going to combine sources so that this reads e to the 8 e to the minus 5t. Now note, like I said, if you look in physics books, that is actually not a correct way of doing it. But we're among friends, and KBL incorrectly calculates the right equation. Okay. Yes. And so what we find here is we saw that this guy, right, is this. And so then I'm going to plug that right back into here. And what am I going to get here is I'm going to get what? I'm going to get this guy here. Note that the inductor is 8. So I'm going to write 8 DIL dt plus 24 IL equals, I'm going to write 8 times the quantity 4 plus e to the minus 5t. So note, because I have that 8 right there, and I'm going to isolate this thing, you'll see that I pulled an 8 out of this equation just to make it easier to see right away. So what I'm doing in here, remember, I need to isolate this guy. So if I isolate this, I've got to divide everything by 8. So I'm going to get di dt plus 3IL equals 4 plus e to the minus 5t. And there's my equation right there. So the question is, when this reaches steady state, what should the current in the circuit look like? Right? At t equals to infinity, the natural response goes to 0, and the exponential source dies off. Right? So the only thing that's left here is the force response. So look at the circuit. This guy has to go to 0. This is 32. That goes as a short. Right? That goes as a short. So what I'm seeing here is that at t equal to infinity, I'm going to get, and then I'm going to have 24. So therefore, the inductor current at t equal to infinity should look like what? 32 divided by 24. So then I'm going to get 32 divided by 24. You guys with me so far? Okay, and you can see here that this should give me what? 4 over 3 amps. Does my differential equation give me that solution? So now, I'm going to check first order equation, or at least one check. So when I look at this guy here, note that we expected the inductor current, so at t equals to infinity, we expect that IL of infinity to be equal to a constant. So if I plug in my constant into here, you can see that I'm going to get what? di of infinity dt plus 3L at infinity should equal 4 plus e to the minus infinity. So you can see that this guy has to go to what? 0. That guy goes to 0. Like we said right here. So then, IL at infinity should equal 4/3 amps. In other words, agrees with the circuit. So that means that at least our constants are good. That doesn't mean that you have the right equation, but it gives you more confidence that you're at least getting something reasonable. Okay, so now that I've checked it, I'm going to go on to step 2. And in step 2 here, I want to determine general response and B1 and B2. Okay, that's what we want to get. So here we go. So what I'm going to do here is that I'm going to go back and look at my solution. So when I look at my solution, the inductor equation tells me I got to have a natural response, right? What's my 1 over tau? I'm going to go over here, and you can see that 1 over tau is 3. So I'm going to walk over here, and I'm just going to write minus 3t. So this tells me here that 1 over tau was 3. I got that right off the differential equation. All right? So now I got to write my force response. So when I look at that, note that that's a constant. That's an exponential. But it's got to be that kind of a burst of minus 5t in the exponential term. So then, let me make sure that I don't screw up here. So I wrote my B1 has to be, I'm going to say that it behaves that way exponentially. And then I get a constant B2. So right now, I have my general response, and I got these two by looking at the effective source term. Right? I looked at that term, this side, that told me the shape of these guys here. So now what do I want to do? I got that. I got my general response. Now I've got to solve for B1 and B2. How do I solve for B1 and B2? I plug them right back into this equation. So what I'm going to do then is that I'm going to come over here. So now I'm going to solve for B1 and B2. So what I'm going to do here is that I'm going to sub forced response into first order equation. Right? I'm going to plug that in. So here I go. So I'm going to write dIf dt plus 3if equals 4 plus 5e to the 4e to the minus 5t. And then I'm going to write if as b1 e to the minus 5t plus b2. Okay, so I'm going to punch these guys into that equation. So let's do it. So if I look at the first term here, so look at this here. If I take the derivative as a function of time, that constant disappears. But if I take the derivative of this exponential term, I'm going to get a minus 5 term that comes down. So I'm going to get what? I'm going to get minus 5b1 e to the minus 5t plus 0. So that's my first term. Right? This term right here is dIf dt. So then I get my second term here, which will be 3, and then I'm just going to multiply by these, so I'm going to get e to the minus 5t plus 3b2, right? So this is the term, this guy right here. And then finally, this has to equal this side of the equation, which will be e to the minus 5t plus 4. So what do? The b's on this side must equal the appropriate term on the right side. So what I'm going to do here is that I'm going to collect b like terms and equate them to right side. So anything that's exponential, I collect. So you can see here, that's going to be minus 5b1 plus 3b1 gives me minus 2b1. So I'm going to get minus 2b1 e to the minus 5t plus 3b2, and that has to equal e to the minus 5t plus 4. So just comparing these b terms here, you can see that b1, if that has to equal 1, it must be minus 1/2. Okay? So this tells me then that minus 2b1 has to equal 1, so that b1 is equal to minus 1/2, and this tells me here that 3b2 has to equal 4, which tells me that b2 is equal to 4/3. So I have my coefficients here, b1 and b2. By the way, somebody came and says, I noticed that you're using b's. Can I use c's? What? Of course you can, right? It's a dummy variable. Apparently you guys use c's in different equations here. So I don't give a damn what notation you use. So then if I write this up here, I now have that the general response now is then ILT. The only constant I'm missing now is A, and you can see that this is minus 3t. I'm going to plug these guys in here, so I'm going to get minus 1/2 e to the minus 5t plus 4/3. So there's really two steps here. Solving for b1 and b2 and writing this equation. So when you write this equation, you only have one unknown constant. Which leads us now to step 3 that tells us go solve for the unknown constant now. So what do? I use the initial, got to find the initial condition on IL at 0 minus to apply it at 0 plus, and then I just apply that initial condition to that equation. So let me erase here. So what I'll do here is that now we're on step 3. We want to determine IC at 0 minus and calculate A. So here we go. So now what I'm going to do, now I'm looking at 0 minus. So at t equal to 0 minus, what's my circuit? Well, at 0 minus, note that this guy's not here. So what is it? It's a short, because it's a voltage source. This thing is open, so then what I'm seeing here is that I have and which direction of current did we say we had? I think we were kind of assuming that the current was going in this direction. Why do we choose that direction? Because when this thing is closed, this was our circuit. So these power supplies had to be applying current in that direction. So if the current is in that direction, and this direction, then we better get a minus sign, and then we apply that minus sign to that initial condition. I mean, to that general response equation. So if I look at this guy here, what I'm going to look at here is I got to do what? So how would you solve for the initial condition of this guy? There's a whole bunch of ways. probably a source transformation might be the easiest thing to go. So what I would do probably, is that I would then go in and write this as well. I'm going to have, so if I look at this branch here, I'm going to have a 6 ohm resistor. I'm going to have a voltage source that then is going to be what? 5 times 6, which then means it's a 30 volt source. So I got a 6 ohm. No, so you can see that the current is definitely going to go in that direction. So if I add these two sources together, I'm going to get a 2 volt source. And then you can see that I got a 24 and a 6 in series, so that's a 30 ohm resistor. So what we find here is we find that IL of 0 minus must be the net voltage, which will be 32 minus 30, divided by the sum of these two resistors, which is 24 plus 6. So it looks like it's 2 over 30, which is 1/15 of an M. And that's what IL of 0 minus is, which is the same as 0 plus. So now I have my initial condition. So now I apply it to our solution right over here. So now we want to apply IC to general response. So here we go. So we got IL of 0 plus gives me 1/15. So if I look at that equation over there, at 0 t equal to 0, I get the A term, I get this. So it looks like a whole bunch of stuff survives, everything survives. So I get A e to the 0, then I get minus 1/2 e to the 0 plus 4/3. So if I solve this thing, I get the equation. What value do I get for A? So I get a value of A that's minus 23 over 30. And this would be amps. So now I have my solution to this thing. So that means then that the complete response is IL of t gives me minus 2330 e to the, what is that, minus 3. And then I'm going to get minus 1/2 e to the minus 5t plus 4/3. So if that's my solution here, I then need to go solve the circuit problem.
Before you erase that, because you solved for IL infinity to 4/3 anyways, don't you already know what V2 is then? Because,
You do.
like if you went to the trouble to do
I
that.
totally, but I'm just trying to be systematic.
Right. No, I totally understand.
Yeah, I'm just trying to be systematic.
If you're going to go to the trouble of solving for I infinity, can you just put that in?
I guess the question mathematically, when you apply that initial condition,
Yeah.
you should,
You already have
that 4/3 also contributes to what?
Yeah.
A. So I agree that, could I come in here and I just write that? But we did that.
Yeah.
I mean, are there shortcuts? Of course there are. So now what we want to look at here once again, if you go on to my lecture notes, I put a lot of details into this. I said, now that you've calculated this, plot this and make sure that this intuitively agrees with what you start off with here. Like for example here, if I was to plot this equation, what would I expect? Well, for starters here, we know that for t equal to 0 minus, this thing is at 1/15. So if I look at this guy here, I have this term right here, and this value right here should be 1/15 of an amp, which is IL of 0 minus. So that means that this guy is coming in right here, and then it starts to charge up. We expected it to charge up because we got rid of that source here. And you can see that as t goes to infinity, that goes to 0, that goes to 0, this goes to 4/3 here. So we would expect this guy to come up, and it should look something like this. So at roughly 5 tau, this thing gets up to 4/3 of an amp, which is IL of infinity. Now, does this make sense here? Well, is this actually true here? So if I do a check here, this tells me that what? IL of 0 has to be what? Minus 23/30 minus 1/2 plus 4/3, and if you calculate that, you get 1/15. So the solution matches up at that condition here. As t goes to infinity, like we already said, it definitely does this thing here. Now, does that make sense? Well, yeah, because we expected that thing to get all the way up there. Now, what we find here is that although the inductor can't change, what about the voltage across the 24 volt source here? So now we need to, step 4, we need to solve the circuit problem. So if I solve the circuit problem, what we already said here, that this guy, because it's in series with the inductor, has to be this thing. Right? And that solution gives me some value here, and if you calculate this value, you get 32 minus 12 e to the minus 5t, and then you get a number of minus 92 over 5 e to the minus 3t volts, and you can see that this is how I get this back. So what is the behavior of this voltage source here? Well, for starters here, what do we expect the source to look like? Well, one of the things that we saw here, initially, the current through this guy had to be the current through the inductor. Right? So we saw here at t equal to 0 minus, we saw that the current of the inductor at 0 had to also be the current of this guy right here. And so when I calculate this guy, this should be what? This should be 1/15 of an amp. So that means then that V24 at 0 minus had to be 24 divided by 15, which then gives me what? 8/5 of an amp. Right? So that's what we mean by this guy right here. What about at 0 plus? Would you expect that voltage to be continuous? I would not expect that, right? Because this is a very abrupt change, right? I would expect a big discontinuity into 24 volt because it's a very abrupt change here. So now, look at me being careful here. 0 minus, 0 plus. So then if I look at 0.24 at 0 plus, well, I got to look at this equation right here. And what does this equation tell me? It tells me that it's 32 minus 12 e to the 0 minus 92 over 5 e to the 0. Right? So when I add this guy up, so right away, this is what? This is bigger than 20 for certain. And you can see that if this is 20, then that makes things this whole thing go to 0, but the fact that this is bigger, it immediately tells me that it's got to be pointed in the negative direction. So when I calculate this guy, what I end up getting here is that I end up getting
It's just under 18. Carlos, I think 92 over 5 would be
I
just over
think
18.
this is wrong, whatever I have.
92 over 5.
Is that the...
Yeah, 92 over 5 is not very.
No. It's smaller, so this guy has to be positive. So I got some crazy number here. What is this number? I get a positive number,
Yeah.
which has to be, I don't know what that number is, so.
1.6, Carlos.
Four point six?
1.6.
1.6 volts. So if I look at this guy here,
It has to be the same.
is that 1.6? Ooh. Why is that the same?
It's in series with the inductor. It has to be the
Because it's
same.
in series with the inductor here. And because it's in series with the inductor, I'm going to see this guy has to behave something a very similar way. So it's got to be coming like this, and then that voltage has to be going up like that. So with this point here, yeah, I have some crazy number in my notes here, which then tells me that this is V24 at 0 plus. And then of course, that value up here has to go to V24 at infinity, which would be 24 volts.
So,
Yes?
so that 8 over 5 is that amps or times 8 or
Ooh, I think I was going off of that. So it would be volts, definitely. Okay, let's go to the next one.